get your notes. Today we are still talking about solving systems of equations, but rather than solving the systems by graphing, now we're going to learn one of the strategies we will use to solve the systems of equations algebraically. That means using equations and not having to graph and find out where they intersect. Okay, so I think I mentioned when we were talking about solving systems of equations by graphing that it's not an ideal way to solve them, but we needed to be able to see visually that the actual solution of the systems of equations is where those lines intersect for each equation, right? So each equation was a linear equation. If we graph both lines on the same coordinate plane, wherever they intersect would be their solution. If they didn't intersect, there'd be no solution. If it was the same line, it would be all real numbers, or we could have said infinitely many solutions. So, why is graphing not the best option for solving systems equations? So we're going to start. You're filling in, following along with me. It's not very accurate. I'm trying to get my board to work. Not very accurate if the lines are very close. So like this example here, we don't really know where those lines intersect. It's hard to determine which point the lines intersect at. And it's hard to graph large values. So it's pretty easy to graph the things we've been working with because they're right around the origin. But to graph things that are in the thousands or hundreds is too difficult. Also, if you're not graphing whole numbers, if you're graphing something besides integers, that's hard because decimals and fractions, it's going to make our graph very inaccurate. It's hard to get a solution if you don't have all integer inputs and outputs. Working with fractions and decimals makes it very hard. We don't like to work with decimals and fractions even when we're solving algebraically, but it's much easier than graphing fractions and decimals. It's hard to graph large values. All right. Y'all caught up with me? I'm trying to hang out over here a little bit so my sound is better on my video. I've been having people say my sound is bad. I tried buying a microphone, it still is not good. Alright, so right now I just want you to watch and see if you can figure out, well, first off, let's talk about, it says solving systems of equations by substitution. What does it mean to substitute something? To replace it. Now, can we just replace it with any old thing? What should we replace it with if we're substituting? Something that's like equal, and that's not just math. It's like if you're on a sports team, if you're a football fan, and your quarterback gets hurt, you're going to substitute that starting quarterback for another quarterback, right? He might not be as good, but at least he is a quarterback, right? So you want to when we mathematically substitute, we're going to substitute for something that has the exact same value, right? So, when we're substituting, the first thing we're going to need to do is make sure that what we substitute with is the same value as what we're substituting for. So, this is the system of equations in example 1. X equals 4 is the first equation. 4 times x minus y equals 75 is the second equation. It is a system of equations. One, they're going to say solve the system of equations and the directions, but also we should know the second equation has an x and a y. The first equation has an x. When they're written together in a pair like that, we assume that they're a system. We assume that the x value in both equations would be equal. Does that make sense, Diane? Okay. So I'm gonna solve this system of equations. I just want you to watch right now, and then I'll give you a chance to write down in a second, okay? So I want you to watch and see if you can figure out what I'm doing. Okay. Anybody see what I did? What do you think I started out by doing, Jacoy? Sure. Okay, very good. One thing I want to correct though, so Jacoy did a really good job of kind of summarizing what I did. She said first off that I replaced the x with 4. So why is it okay that I replace the x with 4? You're exactly right. Jacoy's right. Keishan, why could I replace the x with 4 in this equation? Why was that okay? It's the same variable, it's going to have the same value. And up here, it clearly said that x is 4, right? X equals 4 means that the x value is 4. So if this is a system, then the x value in the other equation would have to be equal to 4 as well. And everything, so once we plug in to substitute, the reason why we want to substitute, for the record, is because we had two variables in this equation, right? We can't solve an equation where there are two variables. But if we can plug in for one of them and get down to only one variable in the equation, then we can solve an equation with one variable. So that's what we did here. We plugged in for x because we need a value, and then we solved for y. So this is a solution to a system of equation. Remember, there's one solution if we were to graph x equals 4. If we were to graph 4x minus y equals 75, the place where those lines would intersect would be 4 and negative 59. Does that make sense, Danielle? Okay. The only thing I do want to point out, so down here, Jacoy said x and y always equal 1. What she meant, I think, is that when we're solving or isolating our variables, the coefficient on x or y has to be a positive 1, right, Jacoy? So with this is the opposite of y. Remember, that's the same kind of as a negative 1y, or negative 1 coefficient. Does that make sense to everyone? All right, I'm going to give you a second to finish writing that example down, and then we'll move on. Now you already wrote it down? Okay. So just like when we were solving a system of equations by graphing, we have three possible solutions. We can have one solution, and then we always get an order of pairs. We could have no solution. When we were graphing that was two parallel lines. We can have all real numbers. That's when the lines are basically the same line, right? You graph one on top of the other one, or just think of them as the same line. So these are still systems of equations, the exact same ones that we were solving last week, but now we're just using a different strategy to solve them. So instead of graphing, we can solve algebraically using substitution. So the first thing we're going to do is we're going to substitute for one variable. And we have to isolate first. Sometimes they're already isolated. In our example, it was already isolated. But sometimes you have to isolate a variable before you can substitute for that variable. Are you following with me, honey? Put that up. Thank you. I'm hoping you'll have a little bit of time to start your homework, but I want you to follow along with me for now. Okay, so once you substitute for one variable, so here we substituted for the x, right? And then we solve for the other variable. So we're going to solve, actually sometimes we have to solve for the remaining, we're going to solve for the remaining variable. And then we're going to plug in into one of the original equations and solve. So our last example was a shorter version because we didn't have to isolate, we didn't have to solve for both equations or variables. So you don't have a spot for this one, so I'm going to have you write it at the bottom. I'll let y'all catch up with me first. We've already talked about the possible number solutions and one solution, which is an ordered pair. And we're going to write that one at the bottom down here. So yours is going to be written down here. So write an ordered pair down here. Because you have this up here. So if the solution is an ordered pair, that's going to be an example similar to the one that we just did. But if it's a special solution, so when the variables disappear, it means we're going to have a special solution. That would be all real numbers or no solution. So if the variables disappear and it's a false statement, that means there's no solution. So, for example, 5 equals 3. That's false, right? So the answer is no solution. So when we solved equations of variables on both sides earlier in the year, and our variables disappeared, we used the same strategy. If our variables disappeared and it's not a true statement, for example, variables are gone, the last thing we have written is 5 equals 3, that's false. None of these are our answer. Our answer is no solution. But if the variables disappear and it's a true statement, that means all real numbers is your solution. So that would look like maybe 5 equals 5. That's a true statement, which means that the answer would be all real numbers. Y'all caught up with me? Okay, so this one was very similar to our first example. The first equation is y equals 12. That literally means that y is going to be 12 in both of these equations. So that being the case, this is a simpler version of using substitution to solve. So everywhere there's a y in this equation, we're going to plug in 12. So 12 is going to go there. So we're going to rewrite this equation to x minus 3, but instead of y, we know now that y is 12. So now we're going to simplify here. 2x 3 minus 12 times 12 is 36 equals 14. With a two-step equation, we're going to undo the subtracting by adding. And that's going to give us 2x equals 50. 2x, remember, is 2 times x. And do multiplying by dividing. And x is 25. So we already know it was given that our x-coordinate is 12. Our y-coordinate is 12. Our x-coordinate is 25. So that would be the solution to this system. We didn't have to graph it. It's very exact. 25 is not a humongous number, but it's a pretty big number if you're having to have a coordinate plane with all those boxes on it. Any questions? Okay. Example 3. So we have two equations. The first one only has a y. The second one has an x and a y. But now you'll notice that first equation, the y is not by itself now, right? So we're still going to start working with that first equation. Whenever we're solving these by substitution, we want to look at our equations. We're going to have to pick something to use as our substitution value. And we want to make that the easiest one to get and the easiest one to work with. So up here, I see that 5 is a multiple of 15. I know I'm going to have to divide if I want to get y by itself. And I only have one variable, so I'm going to start with this one. Because I need a value for x, and I need a value for y. Sorry? Okay. 5 times y equals negative 15, so I need to get a variable by itself so I can use that value to substitute in the other equation. So I'm going to divide both sides by 5. Now I have y equals negative 3. That I can substitute in for the y here. And when I only have one variable, once I've solved for it, or isolated that variable, I also have my coordinate already. So I already know that part of my answer, the y value, is negative 3. So now I'm going to substitute that negative 3 into the second equation. So 3x minus 2 times y, but now I know y is negative 3, equals 8. And then we're going to solve that equation. First thing we're going to do is simplify here. Negative 2 times negative 3 is positive 6. And undo the adding by subtracting. Gives me 3x equals 2, and divide both sides by 3. Now I know that my x-coordinate is 2/3, and I'm going to put that up here in my answer. So this is your final answer. This is all the work you need to get your final answer. Make sense? So if I were to graph the two equations that we started with, 5y equals negative 15, and 3x minus 2y equals 8, they would intersect at 2/3 and negative 3rds. That order pairs. But that would be hard for us to solve by graphing, right? Because it's hard to graph 2/3. Y'all caught up with me? Example 4. Now, I've got two equations. Y equals 2 times x. And x plus y equals negative 3. Now both equations have an x and a y. If I want to use substitution, though, I typically, so we're going to learn other ways to solve algebraically. When we solve by substitution now, whatever they give us, we're going to work with, right? But this would be a good example, a good system to solve by substitution, even when we learn our new the other way we're going to learn. We're going to learn how to solve by elimination as well. But anytime one of the equations is solved for the x or the y, it makes it a very good candidate for substitution. So now, I don't know what the y value is. I can't plug in the y coordinate already, but I do know that y is going to be the same as 2x. So here, well, I don't have a numerical value for y. I know instead of y, I could write 2x, right? Because this says y is the same as 2x. Now instead of y, now we're going to do x plus 2x equals -3. Now, I can't solve the equation x plus y equals -3, but I can solve the equation x plus 2x equals -3 because I only have one variable. So I'm going to add my like terms here and solve for x. So my variables didn't disappear, so right now I know that I have one solution, and I know that x coordinate is -1. How am I going to find the y coordinate for my answer? What do you think? How do we find our y coordinate? It is not 0. We're going to take this -1, so x is -1, and we can plug it into either one of these equations now and solve for y. So I'm going to use this one because it seems easier to me. So y equals 2 times -1, and in fact, because it was solved for y already, now we know that the y coordinate of our solution to this system of equations is -2. And so we know that if we graph these two lines, the point where they would intersect would be -1, -2. Does that make sense for you, Tia? Does that make sense, Gladys? Okay. All right, so now this looks a little bit different. How many tables do we have? 6 or 7? 7. Okay. This one looks a little bit different because now neither equation is solved for x or y. They both do have an x and a y, an x and a y. So if we're using substitution, we have to pick one of these equations and then either get the x or the y by itself. So I look at this equation. Both variables have a coefficient on it. Here, I see the coefficient is 1. So this one has a 5. If I just subtract this 5y, I know I'm going to have my x by itself. So that's what I want to look for. I want to look for the easiest way to isolate a variable. So x plus 5y equals -3. I don't have to multiply or divide anything. I just subtract the 5y from both sides. Now I know that x is the same as -5 times y minus 3. So when it says x equals -5 times y minus 3, we should know that that means it's the same as, right? And so we can use eyes or seeing. So here there's an x. We could also, it should be equal to -5 times whatever y is minus 3. Now here's the trick though. If we use this first equation to substitute, we can't take this and plug it back in there. We have to plug it into the other equation. Does that make sense, Brandon? So since I isolated the x in the first equation, I can't replace x with this in the first equation, but I can replace it in the second. So instead of x, let's go ahead and put parentheses because there's more than one term. Go ahead and put parentheses around that. Now 3 times x. We know x is the same as this, so 3 times -5y minus 3. That is the same as 3 times x. Does that make sense, Diane? Does that make sense, Nicholas? Okay, and now I bring down the rest of my equation. -2y equals 8. So now I am solving for my y coordinates. I don't know which one is which. Right? I don't know. In fact, I'm not even sure it's an ordered period. I want to see, are my variables going to disappear? If my variables disappear, then it won't be an ordered pair, but let's see what happens here. Going to distribute. -15y minus 9 minus 2y equals 8. And just bring those down because we didn't do anything with those. And I'm going to combine like terms. That's -17 times y minus 9, all combined over here, equals my 8. Haven't done anything with that yet. Now I've got a two-step equation. Negative 17 times y minus 9 equals 8. I know I'm going to undo the minus 9. I'm going to first, I'm going to undo that by adding 9. So now I have negative 17 times y equals positive 17. I have a one-step equation. It's being negative 17 is being multiplied by the y, so I undo that by dividing by negative 17. So now I know that y is negative 1. I know that my variables did not disappear, so it's not a special solution. I know that my y coordinate for my answer is going to be negative 1. So up here, I already know part of my answer. You guys need more time? Let me just go back down. Y'all caught it with me? Can you caught up with me? All right, Anson, you good? Make sense so far, Xavier? Not in the little notes, buddy. When we get done, you can. All right, so now, how do I find that x-coordinate? Do you remember, Lee? How do we find my x-coordinate if I know my y-coordinate now? What do I do? Yes, what am I going to plug in and where? Sorry? Okay. What do you think? Cole?
So the equation x equals negative 5y minus 3 and replace y with negative 1.
Yes, and actually in this case I could use either one, but I like Cole's pick because that's a simpler equation, right? So he says I can take this negative 1 and replace y with negative 1 and then solve for x. So that's what I'm going to do here. X plus 5, but instead of y, we're writing negative 1, 5 times negative 1 equals negative 3. We're going to simplify that to negative 5. And then we're going to undo minus 5 by adding 5. And now we know that our x-coordinate is 2. We already knew our y-coordinate was negative 1. Uh-oh. There we go. So this is our solution to negative 1. Any questions? That makes sense, Jaden? Good. All right, y'all caught up with me? Can I move on? Okay. All right, so now we have two equations, 2x plus 2y equals 8, and x plus y equals negative 2. So I need to isolate either x or y. And I'm going to use this one because no coefficients here. Doesn't really matter which one we isolate. I'm going to isolate the y here. I'm sorry, the x by subtracting y. Doesn't matter. We could have isolated the y, but I'm just working left to right. So x, that's going to go to 0, equals the opposite of y minus 2. Does that make sense? So we're going to put parentheses around that because we have more than one term. Now we've isolated x in this equation, so everywhere there's an x in the other equation, I'm plugging in negative y minus 2. Savarian, did you come in? How do you were you here all the whole time? I've got to fix my, I think I marked you absent. My bad. I did. I'm so sorry. The other people, Takori, Peyton, and Tatima. Oh, okay, we'll get there. All right. So now, in this first equation, 2 times x, but now I'm going to use this for x. So this x is the same as the opposite of y minus 2. So parentheses 2 times negative y minus 2. There's a plus. I'm going to add plus 2y equals 8. The only difference here and here is that instead of x, I wrote its substitution value. What is the coefficient on y? We just threw the negative sign there. What's that going to be? Negative 1, right? So sometimes it helps kids remember how to distribute. So we're going to distribute. 2 times negative 1y is negative 2y. 2 2 times negative 2 is minus 4. We do not distribute the 2 here because it's separated by addition, so that's plus 2y equals 8. I'm going to combine my like terms. What is negative 2y plus 2y? What's negative 2y plus 2y? 0, right. So they're opposites, right? So we're going to scratch those out because they equal 0. And what we have left is negative 4 equals 8. So here, our variables are gone. We don't have variables anymore. We say that they disappeared. So now we need to decide, is this a true statement or a false statement? Danielle says it's false. She's exactly right. Negative 5 is not equal to 8. So we can say that's false, but I still have not given my answer. What is the solution to this? Very good. No solution is actually the answer. So you do all this work to get this answer. And we don't have to go back and substitute in again. There's nothing to substitute in, right? We don't have a value. Does that make sense to everyone? Are y'all caught up with me? All right, last one. All right, so which one of these should we isolate a variable in? The first equation or the second equation, do you think? Danielle says the first one. What do you think, Brooklyn? I agree with Danielle. The first one, why did you pick the first one, Danielle? Say that again. Yeah, so that y doesn't have a coefficient on it. So I'm going to isolate that y. That's going to be my easiest math. So let's rewrite that equation. 4x plus y equals 12. And then we're going to get the y by itself by subtracting this 4x. So now that's 0. So y is the same as negative 4 times x plus 12. We're going to put that in parentheses. So now what am I going to do with that? What am I going to do with that to help me solve my system? Okay, Sean? Plug it in the other equation everywhere I see y. So I can't plug this one in here. I'm going to go down here, and instead of this, I'm going to write this. That's exactly right. So 2 times x minus 3 times negative 4 times x plus 12, because remember that is the same as y, equals 14. Now I have an equation I can solve because it's all x's, no y's. So we're going to distribute here. I'm going to bring down this 2x. Negative 3 times negative 4 is positive 12x. Negative 3 times positive 12 is negative 36. And that equals 14. So I'm going to combine my like terms. 14x, bring down my minus 36 equals 14. And I'm going to solve for x. So add 36. And 14 times x equals 50. I isolate my x by dividing both sides by 14. And I'm going to simplify that fraction. 2 comes out of 50 25 times. 2 comes out of 14 7 times. So we don't like to work with fractions. So remember we have a trick to that. But our x coordinate, so we know now there is only one solution. We know it has to be an ordered pair. And we know the x-coordinate is 25 7. We learned that like it, but we know it. So we're going to go up here. Go ahead and put in our x spot 25 7. Now we've got to figure out what our y is. So everywhere there's an x in either equation, now I can plug this in. So I'm going to work with this one again. 4 times 25 over 7 plus y equals 12. I'm going to go ahead and distribute, or go ahead and multiply this. That's 107 plus y equals 12. Now, we don't like to solve equations that have fractions where we've got to change into common denominator. So do you guys remember what we do if we have a fraction and we want to get rid of it? What should we do to get rid of that fraction? Any idea? Ulrich? So we get rid of a fraction. We can't cross multiply this one because we have addition on one side. That's a good thought. Cole, do you have an idea? Danielle? Well, we could turn it into a decimal, but we have another strategy. Keishan? You change your mind? You play? Close. What if so the fraction is what we don't want, right? Alright? Yes, there we go. The fraction is what we don't want. And the denominator makes it a fraction. Think about it that way. So if we multiply everything by that 7, we get rid of that 7 on the bottom. So that's going to be 700 over 7. 700 divided by 7 is 100. Plus, so we did that. 7 times y is 7y. And 7 times 12 is 84. So now I have an equation and I don't have any fractions. It's a little bit easier to solve. I'm going to wind up with a fraction answer probably, but that's okay at the end. We didn't have to turn anything into common denominators. So I'm subtracting 100 from both sides. 7y equals negative 16. Divide both sides by positive 7. And so I know that my y coordinate is negative 16, 7. So now my x coordinate and my y coordinate are both these kind of not great fractions. I could never solve this by graphing by hand, right? It would have been very difficult. It would have had to have a really big coordinate plane. It would have been almost impossible. So let's plug that in our y spot up here. Negative 16 sevenths. So this is our final answer. See where you want to run the bathroom? I know it's almost too late, but you can go. You get out of here in three minutes. That's okay. You'll run out of time. Just hurry back. Okay, so I gotta make sure the assignment is there. Don't forget to scan and submit your notes. I think I put it there Friday.